So this is Ham Hacks, breaking into the world of software-defined radio. Before we really, dive in and get started, I just want everyone to know I'll be posting my slides later today. There's lots of links in here, so don't feel like you need to, be taking notes or screenshots or worry if you miss anything. I also have some demo videos near the end of the presentation, and if the quality is bad or you feel like you missed something, don't worry. All of the videos are available on the Bishop Fox YouTube account. So let's get started. So a little bit about me. I'm Kelly Albrink. I'm a penetration tester at Bishop Fox. We're a consulting company who just does offensive security. And when I'm pen testing there, I mostly do network pen testing and a lot of hardware and wireless security. So far during my quarantine, I've spent it watching Tiger King, 3D printing a bunch of face shield frames for first responders. And as you can see from my image here, spending entirely too many Nook miles for a big satellite dish on my Animal Crossing village. If you want to keep in touch after the talk, you can hit me up on Twitter. My handle's Justified Salt, and I'll also be on the DerpCon Discord as privileged. So, why should you care about any of this stuff? I want to start by telling you a little bit about a story about the guy that's shown in the picture here. This is Heinrich Rudolf Hertz, and he was the first scientist to basically prove the existence of radio waves. And the unit of frequency in our radio is called the hertz in his honor. So when he made this big breakthrough and he was asked about the impact of his discovery, he said, "It's of no use whatsoever." And when asked about the applications of radios, he responded, "Nothing, I guess." It's pretty much the 19th century equivalent of "thanks, I hate it." So why should you care about radios, or why should you get into this at all? Well, pretty much the answer is that from your cell phone to your car keys to your Wi-Fi router to the satellites that are orbiting above us, we're pretty much surrounded by signals carrying information. And it's pretty much magic. So software-defined radio lets you wield that power and learn more about the invisible world of signals that's all around you. So if you learn to become a radio hacker, you're pretty much a wizard. So before we kind of get into the technical stuff, I want to definitely get you guys thinking about some cool projects that you could maybe do by sharing some awesome stories of other radio hackers. So this first one is a presentation from DEF CON 25, and it was called Tracking Spies in the Skies. And it was a group of these 4 guys, and they were using some really, really simple radio hardware, just a $20 RTL SDR and a Raspberry Pi. And they use this to start tracking planes. There's a protocol called ADS-B, and it basically is for navigation so planes don't run into each other, and it broadcasts their route. So anyone who has a software-defined radio can right now turn it on and find out what planes are above them in the sky. So this group of guys, they started looking at planes over Los Angeles, and one of them noticed that there were a group of planes that would take off every day, go to a specific area, and then circle around that one area and then land again at the same airport. And they were wondering, what's going on here? Why are these planes doing it? So they started kind of looking in the FAA lookups for the planes, the registrations, and they were all kind of registered to these 3-letter companies. So you can see in one screenshot here, we have OBR Leasing or XYZ Technology. And they were able to kind of trace the registration back and eventually found out that these planes are Department of Justice planes, FBI planes, and they're essentially spying on people for whatever investigation they're performing. So one of the presenters said, if you're in the middle of one of these circles, it's probably time to get a lawyer. And why would they do this from planes? Probably for photography surveillance, or maybe using a base station like a Stingray to intercept cell phone communications. So this was a really amazing, great piece of research that was done for $20 in radio equipment and a $35 Raspberry Pi. The next one that I want to tell you about is from Sammy Kamkar. He called it Drive It Like You Hacked It. And in this presentation, he wanted to recreate the hack in Gone in 60 Seconds where they wirelessly open a garage door. So garage door openers are typically just an 8 or a 12-bit code. So to guess every possible combination with the standard delay in between codes took 29.5 minutes. But the movie isn't called Gone in 29.5 minutes. It's called Gone in 60 Seconds. So the next step was, how do we shorten this? Like, how do we get this hack to go a lot faster? So one of the first things that he figured out was, how does a garage door know where one code starts and another code, or one code ends and another code begins? And he found out that essentially it doesn't. It's just constantly listening to get the right sequence to open the garage door. So he used something called the De Bruin sequence, and it basically shortened the amount of guesses that he had to do by concatenating all of the possible combinations together in one long string. And he got this guessing the garage door code down to 8.214 seconds. I actually think in some later presentations, he got it as fast as 6 seconds. So now that he has this great program that can brute force any garage door, how does he actually transmit those signals and prove that it works? And that's where this pink toy that you see on the screen comes in. This is the Mattel I Am Me. And this was like a little, $25, $30 toy that had a sub-gigahertz transceiver in it. And at the time when he was doing this research, there wasn't readily available cheap radio technology. It was actually pretty expensive. So he figured out that he could reprogram this Mattel toy and use the radio hardware that was inside to perform his garage door attack. So these days, if you want to get your hands on one of these Mattel I Am Me toys, they're like $200 or $300 on eBay because they've kind of become a part of radio hacker history. But luckily, we have access to a lot more cheap and great radios now, so we don't need to kind of hack together on some old toys. There's two quick talks that I want to bring to your attention because I think they're awesome. One is by Balint Sieber from Bastille. He has a lot of really amazing radio talks, but one of my favorite is where he rickrolled all of San Francisco using the emergency broadcast radios. And if you want to see that, you can see his DerpCon talk, All Your RFZ Are Belong to Me. Another really fun DerpCon talk that I love for radio hacking was by Kristen Paget. And she basically owned an entire room full of people's cell phones by creating her own base station or stingray with software-defined radios. So any call or any text message that was sent in that room during the presentation was intercepted and essentially man-in-the-middled by her. And the reason she was allowed to do this was because there's some crossover between the GSM cell phone band and some amateur radio bands. So if you become a licensed amateur radio person, then you could get to do some really cool, interesting experimentation in these crossover areas of the spectrum. So those are a couple really cool war stories and awesome radio hacks that I hope inspire you to get more into it. And let's just kind of dive in and start figuring out how we can do it ourselves. So today we're going to talk about a couple things. We're going to go over some radio basics. We're going to define some common terms so you know what words to use when you talk about radio. And then we're going to go over what the different RF bands are in the spectrum and what they're used for. Next, I'm going to kind of give you the hard and fast intro to the hardware and the software that you're going to need to actually do radio hacking. And then at the end, we're going to go through a demo. We're going to find a signal, we're going to record it, and then we're going to start reverse engineering it. And that signal is going to be from a car key fob. So we're not going to talk specifically or in depth about ham radio hacking, but I do really want to encourage everyone to get involved in ham radio because it's one of the best ways to learn about radio topics and really become like a more advanced radio hacker. So let's start off with some RF basics. So when we talk about radio waves, there's two main ways to describe them. There's the wavelength and the frequency. The wavelength is pretty simple. It's the distance between the peak of two waves. And it's actually measured, as a distance. It's typically referred to in meters or centimeters. And then there's also the frequency. And the frequency is how many waves pass per second. So if you time for 1 second, how many peaks of those waves will you see? Since all RF waves travel at the same rate, which is the speed of light, the frequency and the wavelength are linked. If we know the frequency of a wave, we can do some math, and then we can figure out its wavelength, and vice versa. So in this talk, we're mostly going to be referring to radio signals by their frequency, but in ham radio, it's pretty common to refer to different RF types by their wavelengths. So we have a couple examples on this slide. You can see at the top, we have a really long wavelength, right? And that's going to be a low frequency signal, low energy signal. Whereas the examples on the bottom have shorter wavelengths. That's going to be a higher frequency, high energy signals. So modulation is the next kind of thing we're going to talk about, and it's how we add information into a radio wave. And some of the examples that you see here on your screen are different common types of analog modulation. So the first one, on-off keying or pulse modulation, is basically what you think of when you think of a telegraph and Morse code, right? When you push down on a button, it sends out a wave, and when you let go of the button, that wave stops being transmitted. And by varying the pattern, we can add information and convey a message. Amplitude modification or modulation, it changes the amplitude or the height of the wave. So this is what's used in AM radio, some older kind of analog TV signals, if you think of like the bunny ears on your TV. And it's pretty good for long range transmission, but it has some kind of fidelity problems. You can have some kind of static or interference. So a little bit more modern way to modulate analog signals is FM, frequency modulation, just like your FM radio. And that changes the frequency or how many waves pass per second to carry information. And then the last example we have on this slide is phase modulation. So that changes the start or the end point of a sine wave to indicate data. So the amplitude or the frequency doesn't change in phase modulation, it's just the start and end of the wave shifts forward or backwards. So those are all some kinds of common analog modulations, but when we're doing radio hacking, when we're looking at IoT devices, we're typically going to be dealing with digital modulation. So let's look at a couple examples of that. So you're basically going to get the same modulation methods as we had in the analog. It's just going to be encoding a 1 or a 0. So amplitude method would be called ASK, or amplitude shift keying. So you can see here the amplitude of the wave is changing to be really high and then to be really low. So that could be a 1 and then a 0. Same kind of principle here for frequency shift keying. The pulses that are representing a bit will have a higher frequency and the zeros will have lower frequency. And then the bottom one, phase shift keying, right? The changes in the phase of the wave are going to indicate where your data bits are. So that's modulation. That's how we get info into a wave. So let's talk a little bit more about what the RF spectrum looks like. So two signals transmitting at the same frequency at the same time will cause interference, right? So in order to prevent problems, the RF spectrum is divided into bands. Bands are basically just a range of frequencies that are allocated for a specific purpose. And since radio waves have different properties at different frequencies, some bands are better for communication, for example, underwater or over long distances, while other bands are better for signals that are just in line of sight, or maybe a signal that has to penetrate a building where there's a lot of objects to get in the way. So while certain portions of the RF spectrum are sold for commercial uses, there's others that are reserved for amateurs, and that's where the ham radio license comes in. So let's kind of quickly go over what some of these bands are and what they're used for. So this one's down at the bottom is not something you're typically going to interact with very much. This is the lowest band is called VLF or ELF, depending on who you ask. And that's for very low frequency or extremely low frequency. And you can see this range is about 3 to 30 kilohertz. And we also have the LF band, low frequency band, from 30 kilohertz to 300 kilohertz. Most of the stuff you're going to see in this range is for government use, a lot of maritime radio navigation and submarines. And the reason that they use these types of waves is because they can travel over really far distances and they can travel underwater. But what they can't do is pack a lot of information into those waves. So let's jump ahead to MF, medium frequency. So this is where your AM radio lives, where some of your aviation radio, and that's in the 300 kilohertz to 3 megahertz range. When we jump up to the next band, to the HF band, that's where things start to get definitely more interesting. HF is what most people think of when they think of amateur radio or shortwave radio. You're going to have your higher frequency NFC, RFID tags kind of in this range, and you're going to have weather broadcast. If you're just getting into kind of amateur radio and your RTL SDR, picking up a weather broadcast is really cool. It will actually like transmit a detailed map with weather information directly to your computer, and you can rebuild those images. Really fun and fascinating. This next one is VHF. So that's where your FM radio lives. That's where VHF television lives. VHF is a little bit of an older television image spectrum. And then the next one is where a lot of the interesting stuff happens. This is UHF, ultra high frequency. You might remember the Weird Al movie, UHF. And it's called that because the television broadcast where the station where Weird Al worked was using an ultra high frequency. So this is where most modern RF tech lives. You're going to get your 2.4 gigahertz Wi-Fi. Your Bluetooth is going to be in here. Microwaves resonate in these frequencies, GPS. Some of your mobile signals are in this range for like 4G. Car keys, which we're going to be looking at later, and RC toys, a lot of drones live in here. So there's a lot of really interesting things happening in the 300 megahertz to 3 gigahertz kind of range. So these last two, I'm going to lump them together because I think they have a lot of common kind of applications, but this is where your 5 gigahertz Wi-Fi lives. You have a lot of satellite and radio astronomy, and the very dangerous, scary 5G cellular signals are here. So super high frequency, that's 3 gigahertz to 30 gigahertz. And then we have extremely high frequency, 30 gigahertz to 300 gigahertz in this range. So that's kind of an overview of what all of the different bands are, what they're used for. And part of radio hacking is kind of figuring out where the signals that you want to reach are. This is kind of a good time to stop and talk about becoming a ham. So if you get your amateur radio license, then there's 3 different levels. There's a technician level, a general level, and an extra level is the highest. And each license basically just allows you additional frequencies and privileges that you can transmit on. So if you become a ham, there's lots of different fun things that you can do with your radio license. There's contests. So a contest could happen at DerpCon. There's fox hunting, where you use directional radio finding to basically hunt down a fox or a transmitter. There's DXing, and DXing is really cool. It's where you try to send a signal over really long distances and have someone hear you at the other end. Another thing that I really like about ham radio is called QSL cards. A little bit old-fashioned, but if you make contact with someone over a ham radio channel, they might want to exchange one of these cards with you. And they're essentially just a postcard that has the person's call sign on it and says that you talk to them, and a lot of people collect them. There's some really fascinating ones out there. There is a ham radio on the International Space Station, and you can actually go call up to the astronauts that are on the ISS, and they have their own very cool QSL card. For us, hacker people, we're probably more interested in some of the more modern ham radio stuff. So for that, I would point you at Packet Radio and Echolink. And Echolink basically, it lets licensed radio hams talk to distant stations over the internet. So that's kind of just ham radio and the different bands in a nutshell. But what are we talking about when we talk about software-defined radio? We've covered the basic terminology, we've gone over the spectrum. So what's software-defined radio? Well, let's start by looking at some of the traditional hardware radio components. So a traditional radio is pretty much always going to be made up of the same common parts, right? You're going to need an antenna. There has to be something to transmit and receive radio waves. So this started as kind of two separate components, the transmitter and the receiver. But in modern tech, they're pretty frequently combined into one device called the transceiver. You're also going to need components to modulate or demodulate your waves. You might have something that's like an amplifier to boost a quiet signal so that it's louder. Or you might also have filters, right? Get rid of noise and interference. So in a traditional radio, this is all going to be their own discrete hardware components. You're going to have circuits of resistors, capacitors, and inductors that are working together as a specific filter or amplifier at a specific frequency. So traditional radios are typically purpose-built to do a specific task at a specific frequency range. And if you want a device that can do a lot of different things, it gets really expensive. But what if you could write a program that would simulate those different radio components in whatever configuration you wanted? That you could change that configuration at a touch of a button and it would run on a $20 piece of hardware. That's pretty much SDR in a nutshell. So the screenshot we have here is of GNU Radio Companion, and this is a program that's a way to program your SDR. So this image is called a flow graph, and each one of these little blocks represents some kind of program variable or radio component, and we can build a flow graph in GNU Radio Companion and then execute it on our software-defined radio. Super useful for rapid prototyping transmitters or receivers. So in a nutshell, software-defined radio is basically just a method to abstract some of those traditional hardware components with software. So you can have one device that does lots of different things. Okay, so what do you need in terms of hardware to get started? So here's the part of the talk where I basically turn into like a shady radio dealer and try to convince you to buy a bunch of potentially very expensive toys. But the good news is that these days you don't really have to spend a lot of money to get started. This wasn't always the case. So before 2010, most radio equipment was just prohibitively expensive for hobbyists to hack on, right? We saw Sammy Kamkar had to use a Mattel toy as his transceiver. But right around 10 years ago or so, some smart people realized that there was a specific Realtek chipset that was used in many common TV adapters that could be reprogrammed as a wideband SDR receiver, which is why we have these awesome RTL SDR dongles for under 25 bucks today. So the RTL in RTL SDR stands for Realtek, which is the chipset. So what's the most important thing when you're choosing which SDR platform to buy? Well, the most important thing is to remember, get the radio that does the job you want it to do. So here are some of the four kind of most common features that you might find in a software-defined radio. The first one is the most obvious, the tuner range. What frequencies can that radio actually see and talk to? If you're trying to catch a signal that's on the 2.4 gigahertz range, but your radio only receives up to 1.7 gigahertz, you're gonna have a bad time, right? The next one is transmit capability. So it's great that there are a lot of these super accessible, cheap radios, but most of the really cheap options are receive only. So it means you can only listen to signals. You're not going to be able to send out your own signals. If you want to move up a little bit into kind of a little bit more expensive radio, then you're going to start to get transmit capabilities. But you have to consider whether you're going to have half duplex or full duplex. Half duplex is basically, it can only transmit or receive at one time. It can't do both at once. Whereas full duplex is it can transmit and receive at the same time. So if you wanted to listen to a signal in the air, intercept it, and modify it and immediately transmit it again, you would need a full duplex radio. So the next kind of feature that we want to talk about is sample rate. Sample rate is how many samples per second. And in software-defined radio, that's typically one sample taken at every hertz. So if you wanted to view a signal with a 20 megahertz bandwidth, it's 20 megahertz wide, then you would need a radio that can capture at least 20 million samples per second. So the best way to kind of think of sample rate is if you were given a project by your teacher to measure the temperature in your backyard, If you just went outside and you took the temperature once per day, that wouldn't be super accurate in terms of observing overall changes and trends. But if you went outside and you took it once every hour, you'd have a lot more data in terms of the changes. And the same kind of thing applies to the sample rate with your radio, right? It's an analog wave in most cases that we're converting into digital information. So the more samples we have, the more accurately we can represent the analog signals that are coming in. The next one is dynamic range, or the ADC resolution. And this is kind of also related to sample rate. So this is how many bits are encoding each sample that you take. You have more accuracy if you have more bits per sample value. So in the same temperature example that we just talked about, if I measure the temperature in just whole numbers, it's not as accurate as if I measured to the second or third decimal place. Software-defined radios typically have a dynamic range between 8 and 16 bits per sample. So let's actually look at some of these radio options and start comparing them. The first one that we have here is the RTL SDR. And this is more a generalist kind of description. There's lots of manufacturers, but an RTL SDR is any radio that's using that specific RTL chipset that allows us to tune to a pretty wide range. The tuner range I have here might vary a little bit depending on what model you get, but you can typically expect an RTL SDR to be able to receive between 50 megahertz and 1.7 gigahertz, which for $20 is actually really, really good. The one kind of gotcha with RTL SDR is that it's receive only. Your sample rate there is 3.2 million samples per second. So that means you're going to be able to see 3 megahertz of bandwidth at one time. Now, if you're trying to capture a signal with a wider bandwidth, like, for example, you're trying to capture a Wi-Fi signal, which has a bandwidth around 20 megahertz, then obviously this isn't going to do it for you. You're not going to be able to see the entire signal at the same time. The ADC on an RTL SDR is about 8 bits, 8-bit unsigned integers. And the most important thing here is the cost, right? This is an amazing value for a radio. It's a great entry-level device. It usually comes with some antennas. There's lots of different options. I probably have, 3 or 4 of these in my radio kit. The next option, if you want to spend a little bit more money, if you need a little bit more features, is the HackRF one. This is in the 10 megahertz to 6 gigahertz range. Awesome range there. And with this radio, you start to get the transmit power. So you have a half duplex. You can either transmit or receive at the same time. 20 million samples per second is pretty good. For most of my purposes, that's absolutely enough. And you can typically find this radio for around $300. So the next two examples are from Lime SDR. We have the Lime SDR and the Mini. Those are a little bit newer to the scene, but their hardware offers a ton of features at competitive prices. There's not for documentation, but it is one option. And then finally, I have on here the Blade RF. This is one of the newer versions of the Blade RF, 47 megahertz to 6 gigahertz. So another huge range. And the benefit here is you have full duplex and 4 channels. So you can transmit and receive on 2 channels for each transmit and receive. 61 million samples per second, 12-bit signed integers for your ADC. Costs a pretty penny at $480, which doesn't include a case or antennas. But I think it's a really great radio if you want to get into some more advanced radio hacking. Okay, so next is, let's talk about antennas for a second. We could spend like weeks talking about antennas. It's a really complicated subject, but you can actually just make your own antenna with wire, and this little thing you see here on the bottom left is called an antenna balun. You can do it yourself. So the antennas that we have kind of in the middle here, those are our basic indoor antennas. That's what you can expect to receive when you buy an RTL SDR. You have a telescoping antenna where you can kind of change the length of the antenna. The one here on the right with the 2 little bunny ears, that's called a dipole antenna. And the important thing to remember when you're using these antennas is indoor versus outdoor, right? If you're trying to catch an outdoor signal, obviously outside's going to receive a little bit better. And if you're using one of these telescoping antennas or these antennas where you can kind of like shift it around, you want to remember that it's going to receive best if you position it in a size that's related to your wavelength. So say, for example, you were trying to catch, you know, a 1090 kilohertz signal. That's about 27.5 centimeters. So if you take your telescoping antenna and you set it to a fourth of that length, about 6.9 centimeters, you're going to have the best results. Another thing to keep in mind is the polarization of the signal that you're trying to receive. Most terrestrial signals here on Earth are horizontally polarized, meaning that your antenna is going to be aligned perpendicular to the ground, whereas most satellite signals use different types of like circular polarization. You'll need a special antenna for that. So let's quickly talk about some of the software that we're going to see in our demo. The first one we've already taken a quick look at. It's GNU Radio Companion. It's basically your custom radio software building tool. This is the GUI version. The companion part means that you're working in a GUI and not just programming with GNU Radio on the command line. So this is a really simple way to start linking things up together. You can use flow graphs basically to create the software, and it supports tons of different kinds of SDRs. Great for your rapid prototyping, and it lets you basically do anything you could possibly want to do with the radio. Two resources I'll recommend here. There's an amazing series of books called Field Expedient SDR. Currently 3 books are out, but I think there's a 4th on the way. If you've ever been intimidated by GNU Radio Companion, then this is the book series that will totally help you get over that. Another really great resource is from Mike Osman. He's the creator of the HackRF and the founder of Great Scott Gadgets. And he has a video series that's all about software-defined radio, digital signal processing, and you don't need a HackRF specifically to go through this course. The next one we're going to talk about is GQRX, and this is a spectrum analyzer. It's going to let you kind of visualize what's happening in the radio world. You can kind of see it's broken up into a couple different sections. On the top, where you see a black background with a white squiggly line, that's your FFT plot. Those squiggly lines represent RF noise, and then when a signal comes through, it'll cause a spike or a peak to form at the frequency it was received on. And the bottom is called a waterfall plot. So it shows the changes in frequency over time. So a signal will look like a red or a yellow dash kind of surrounded by blue. GQRX can not only listen, but it can also record signals too. And the best place to learn more is actually from the creator. He has an awesome cheat sheet and video series, which I've linked here. So the next one is Inspectrum. This is where we're starting to do kind of some of our analysis steps, right? One of the things we're going to see in the demo is that we find the symbol rate. Symbol rate in radio hacking is kind of like the equivalent of like the baud rate in hardware hacking, if you're familiar with that. But this tool is basically going to help us go from a signal to actual bits, to ones and zeros. So if you want to get more into Inspectrum, there's not a ton of tools out there and resources out there, but Mike Osman specifically covers it in episode 11 of his SDR series. And there's also a really great video on Cyberspectrum episode 8 that goes over a whole reverse engineering workflow and uses Inspectrum. And the last tool that we're going to go over is my favorite, Universal Radio Hacker, or URH. It's pretty much got everything. So you can actually like locate and record your signals like we did in GQRX. You can go from the signal to the bits like we did in Inspectrum, but then it adds this whole other layer of analysis. So you can actually start reverse engineering at a protocol level what's happening. You can start identifying fields and their length. You can color code them. You can compare different transmissions that are received. And then the coolest part is that you can actually use this to modify those signals that you reverse engineered and then transmit them out again in your attacks. So the best place to learn more about this is also from the creator, Johan Pohl. It was his like master's thesis project, and it's super awesome. I'm excited to show it to you. So let's actually do it. Let's jump in and put everything together that we've talked about so far. Since one of the most common areas of research in hardware and wireless is car hacking, I was super interested in trying it out. But I live in San Francisco and I don't have a car. So I started wondering, what happens to all of the car key fobs that get left with the valet drivers, right? Most cars come with 2 fobs, and people lose and have to replace them all the time. So where do all the lost car key fobs end up? The answer I found was eBay. I bought about a lot of like 20 car keys for around $2 a key. And I waited a little while for a lot that had a good variety of like manufacturers and ages. And when I was just starting to learn and get into radio, looking at these car key fob signals is exactly where I kind of dove in. So let's go through it together. We're gonna find the signal, we're gonna record the signal, and then we're gonna analyze it. And the goals here is basically to get to the high level protocol at the end, right? We're gonna have to identify a bunch of different things. We're gonna have to know the frequency and the bandwidth of where we can actually find our signal. We're gonna have to know what type of modulation is it using so we can demodulate it and get that information out. We're gonna have to figure out the symbol rate, so how fast it's transmitting, kind of like the baud rate, remember? And then from there, we're gonna go up to like the protocol level and start rebuilding the packet. So the packet structure is gonna have a lot of different things. It's gonna have something called a preamble. Preamble is kind of like the teacher clapping her hands to get the class's attention. And then it'll have a sync word. The sync word is kind of synchronizing the clocks between the 2 different devices that are talking. We'll have a CRC, which is like a checksum. And then ultimately, we're going to try to identify what are the different fields and field sizes. So step 1, first thing you have to do is find the signal. And the easy way to do that is if your device that you're testing has an FCC ID on it. Every basically test that does radio communications has to have an FCC ID and go through a round of like testing. And a lot of that documentation is publicly available. So if you have an FCC, you can look it up on fcc.io and then quickly identify a bunch of information about the device. Some of the stuff that you might find, for example, like immediately here, we can see I looked up one of my car keys and it's transmitting at 315 megahertz. We already know exactly what the frequency that we're looking for is. Other stuff that you might find is like user manuals that tell you exactly how the device works. You may also have like a testing report, which tells you what type of modulation they're using. And you could also get internal photos of the device. So you can start to like figure out what components are in use, maybe look up their data sheets, all super valuable information when you're testing a radio device. But what if you don't have an FCC ID or you're doing kind of like a black box test? That's where GQRX comes in. So I'm gonna go ahead and kick off a little video here and we can see GQRX in action. So you can see I actually had it tuned to around 97 megahertz. And if you look at 96.5 megahertz, that's an FM radio station. And we can actually add demodulation right here in GQRX and listen to the radio. But in this case, we're trying to actually confirm what our car key signal is. So I'm going to change it over to 315 megahertz. And once we tune into that range, you can see the bottom half of our diagram, the waterfall plot, is all blue. It's not receiving a lot of signals in that area. I turn off the modulation and then I start pressing my car key. And I have a couple different car keys, so I'm kind of switching in between them. And you can see a couple different types of signals are coming down into this yellow area. So we've confirmed that we've successfully located exactly where the car key is. And I even zoom in so we can get a super accurate read on exactly where it's transmitting. So GQRX is a really great kind of overall tool. It can also be used to record signals and save them, but I'm going to show you a couple different ways to do that. So now that we know where the signal is, it's time to make a copy of it. There's basically every radio has its own command line tool to do it, but I'm going to show you the RTL SDR version because it's pretty simple. And to record the signal, we have to know a couple different things. We have to know the frequency where the signal we're trying to record is located. We have to know the sample rate, so how many millions of samples per second, and then the number of samples to read. So that's going to tell us how long of a capture in terms of time that we're actually recording. Gain here, usually the default or it has an auto gain setting, but it's basically going to describe the power level of the antennas or amplifiers in your radio. You don't typically have to mess with that too much. And then you're going to save all of this to an output file. C file, capture file, is just the standard format. but depending on your radio, you might use a different format like CU8 or CS8, just to say what type of dynamic range recording it's doing. So let's say we've done all that, right? We found our car key signal, we recorded it. Let's do the analysis portion. And I'm going to start with Inspectrum. Inspectrum's pretty simple, not super full featured, but I've loaded our car key signal into this area, and we're going to see little green blips against the black background. Those are actually the transmissions from our car key fob. And I'll zoom in. The one kind of tricky thing about Inspectrum is every time you zoom, it's going to scroll you to one end or the other of the capture. So it's a little tricky to navigate. But we can already see kind of a repeating series of same length bits. It's called the preamble, right? The teacher clapping her hands. And then later, those bits become a little bit more varied. That's actual data. So I'm going to change my sample rate to match my recording. And then I'm going to start trying to figure out what the actual symbol rate is. So to do that, I'm adding an analyzer. And this is basically just an amplitude threshold. So you can see I have this little white bar with a red line in the middle, and I'm going to move that over my signal. And then down below, you can see in green, this is actually kind of like a more clean analysis. From there, I'm going to derive it into a threshold plot. And this just kind of cuts everything off at the top, so it's nice. We can really clearly see our data here. From here, it looks like it got cut off in the video, but you can export this to the ones and zeros on your command line or to an output file. So essentially, we've gone and done from the signal to the bits in Inspectrum. So to kind of get that data all correct and accurate, I'm going to add some cursors here and move them until they're exactly hugging either side of each one of these little green blips. The advice I have for you here is don't start with a ton. Don't start trying to do your entire signal and make it match. Start with 10 or 20, get it to line up, and then add a little bit and kind of recenter as you go on. I'm a little bit cheating here. I know there's 270 or 271 symbols in this block of transmissions, but you can see I spent a little bit of time kind of trying to get everything perfectly lined up. So let's jump ahead and look at Inspectrum since we're coming up on the end of our time here. This is hands down my favorite tool, super easy to use. And you can see this is the exact same key capture. We have 4 button presses that we've captured, and we can zoom in, zoom out. We can see the kind of preamble section that's a little bit separated out. And it's really easy to just like crop and edit your signal. So I'm just going to highlight the section that we're interested in and then delete everything else out. So the first thing we're going to have to do is we know that this is amplitude modulation, right? ASK. So we're going to change our modulation type and then zoom in a little bit on the signal. The next thing we're going to try to figure out is the symbol rate. It's a little different in Universal Radio Hacker. I'm going to highlight just kind of one of the shortest pulses. And I see it's around 950 or so samples. And I'm going to round that up to 1,000 and put in an error tolerance of 50. So we can know that's basically like the shortest pulse that we'll see. Now we're not really getting any kind of analyzed data in the bottom section. So let's kind of switch our view into the demodulated view, and we'll start playing with the noise and the center. So I want the center to be a lot lower. You can see there's that green portion. Everything that's up in that green area is going to get picked up for analysis. And everything that's below in the purple, or now the red portion, is going to be our noise. If we zoom in, we can see this is kind of the noise floor, all that interference from our radio recording. So we can go ahead and just really narrow that down so it's not important. So now you can see in this kind of like box below, we started to get data, right? We can take all of these ones and zeros that we've kind of converted from our signal. We can start to analyze them in the next tab. That's the analysis tab. So the really cool thing here is that it's just super easy to interact with. And we've kind of gone from signal to bits way faster than we did in Inspectrum. So in analysis, we can, wow, sorry, this is coming through a little bit jumbled. There we go. So in analysis, we can view the data as bits, and we can see it's already separated it for us into like different packets. And just going to bits isn't actually the most important thing. We actually have to decode those bits, right? So you could do Morse code. The most common one you're going to see in IoT devices is Manchester encoding. But the really great thing about URH is you can make a custom encoder or decoder. If you just observe a pattern that you think is right, or maybe you see it in documentation, you can save and make your own. It's super adaptable kind of software. So I've made my own custom one here based on some of the data sheets that I looked up for this key. And you can see now we've kind of decoded all of our long ones and zeros, and this is the actual data that we're going to be interacting with. I switch over to hex and we can see that preamble 7878, it's repeating, right? That's basically telling which specific car it's talking to. And then we have some other longer packets. And if we check off mark diffs in protocol, that'll show us what all of the differences are. The great thing about URH is you can start kind of like at a protocol level highlighting certain fields. So I'm going to say, okay, the first 2 bytes are going to be our preamble, for example. Maybe I know that from documentation. Bytes 3 through 12, then that's going to be kind of like our actual data of the packet. And then our last 2 bytes, that's going to be like a checksum or our CRC. So URH, super powerful tool. Something you might notice here is that every one of these packets is exactly the same. So what does that mean in terms of our car key? It means that this is a completely replayable signal. It's not a rolling code. It's not changing every time we transmit. It's something that's like, just if you record this signal once, you're going to be able to replay it and unlock the car. So there's also the generator and the simulator tabs. I don't have time to really go too much into those, but generator is basically where you can create new signals based on what you've already reverse engineered. And then simulator actually lets you like transmit and send out those signals. Cool. So that's kind of in a nutshell what you need to know to get started with this stuff. And I know it's super intimidating and kind of scary to go through all of these programs, but it's actually really, really simple when you start getting into it if you have access to the right resources. So I'll share a couple additional resources with you here. The top one I'll call out specifically for the wireless village. There's an awesome group of people that organize wireless villages at different conferences around the country. And they have their own Discord channel. They have some really great resources online, and they also do really fun CTFs. So if you're at a conference where the wireless village is attending, definitely check if they have a CTF, because it's not just Wi-Fi hacking and Bluetooth hacking. It's also places where you can practice your software-defined radio skills. The RTL SDR blog is another great resource. It's kind of like Hackaday, where people post different projects and tools. And then if you do want to become a ham and get your ham radio license, the best way to study is called Ham Study. And they have practice questions and tests. Absolutely #1 resource for becoming a ham. And then finally is the RTL SDR subreddit. That's a pretty active community as well if you want to start getting into this stuff. So that in a nutshell is how to get into software-defined radio. Do we have any questions?
That was awesome, Callie. Thank you. I'm gonna have to look at this video again just to wrap my head around a lot of these concepts, but that is really, really good. I think we had a few questions from Discord webinar. So I think first off, Gundam 101 asks, is it possible to get the fob frequency in one try if we don't know what frequency it's working on?
Yeah, so most of the devices that you're actually going to be testing, it's super easy to find the frequency of what it's transmitting at if you just do a little Googling. So car keys in particular, in the United States, they're almost always at 315 megahertz, but in Europe, they're more commonly at 433 megahertz. So it's kind of doing a little Googling, you can kind of eliminate a lot of the frequencies so you don't have to look at the entire spectrum, but it totally depends on what device you're testing.
Awesome. Thank you for the question. Major asks, what's the difference between sample rate and symbol rate?
Sorry, could you repeat that?
Oh yeah, no worries. The mayor asks, what's the difference between sample rate and a symbol rate?
They're just kind of, so the sample rate is how many samples are being recorded, and the symbol rate is how many actual like ones and zeros are being transmitted and at what speed. So the sample rate is more for like programming your SDR specifically, but the sample rate is part of the protocol. And if it's easier for you to, if those terms are too similar, instead of the symbol rate, a lot of people call it the data rate. So maybe easier to think of it as the data rate. It's like how many actual bits are going by per second.
Awesome. And then we also have a question in GoToWebinar from Dominic, who asks, at what point do you need an amateur radio license to continue in software-defined radio hacking?
That's a great question. If you just want to receive and listen, you typically don't need an amateur radio license for that. When you start wanting to get into more active testing where you transmit information, that's when a radio license can come in really handy. So that's when you would need it. But I encourage you to kind of go for it anyways, because it's an amazing community of people that definitely want to like help you learn and teach you. And it's going to make you a better hacker when you really understand what's happening behind the scenes.
Awesome. And also a question from James, who asks, since RF1 and Lime are same price, what kind of projects could you do with their different ranges? Is one better for a beginner?
I definitely think the HackRF is better for beginners. The community is really great. The documentation is awesome. There's tons of examples online. So if you're kind of looking for your first like, kind of expensive radio, I would definitely say go for the HackRF. It's totally open source hardware. There's some great other like modifications that you can do to it, like the HackRF Porta Pack. I definitely, like for entry-level radio people, recommend that because it's the easiest to get started with. You'll know when you run into the limitations of the HackRF and you start wanting more advanced equipment.
Awesome. And just to remind everybody, all the talks are being recorded. Slides will be available end of the day, hopefully today, if not in a day or so. The videos of the talks will be uploaded hopefully by next week on YouTube. We might take a little bit more, but we're hoping to get them up by next week on YouTube. So yeah, that was a great talk, Kelly. And unless everybody has any more questions, I think we're gonna call it. And just a reminder to not exit the webinar. I'll boot you out in a second. Since we have one more minute, we actually do have a minute for another question. And Technopreneur asks, nice, thanks. Any thoughts on sigintos.com, which Kelly would have to get back to you on that probably. I'm not sure if she can just put it up right now, but yeah.
Yeah, I mean, that's a really cool resource, and there's lots of other awesome resources too. I'll post some links to my favorite ones so we can kind of chat more about it. But yeah, awesome. If you're trying to like identify an unknown signal, that's a really great resource to kind of figure out what's going on.